Hey everyone, so in this video I want to introduce something to you guys called the natural logarithm. Now before we start talking about the natural logarithm, there's a couple things that I'm going to need you to remember. So for example, I want you to imagine that we have an expression like b to the power of a is equal to c. So this would be an expression that we would consider to be in exponential form. Now, you should be able to recall that if we have an expression that's written in an exponential form like this, we can actually rewrite it in a completely different way. All right, and that other way is going to look like this. So log base b of c is equal to a. And this is going to be what we're going to call logarithmic form. So the idea is that if I have an expression written in exponential form, I could convert it to logarithmic form, and technically I could do it the other way around as well. If I have something that's written in logarithmic form, I could rewrite it in exponential form. Another piece of information that I'm going to remind you of is something that I would have discussed with you already, and that would be that we have a special number, e, and e is approximately equal to 2.718. Remember that we call that Euler's constant. And the reason why it's important is because when e is the base of an exponential function, then if we take the derivative of that exponential function, it will be equal to the original function. So that was what I introduced to you before. We were basically looking at the function y is equal to e to the power of x. And again, we discussed the derivative of this function, and the derivative of this function ended up being itself. So the idea is that y is equal to e to the power of x is going to be a very special function. In fact, if you take a look at a scientific calculator, you should be able to find a button somewhere on it that has e to the power of x, or e to the power of n, or something along those lines. All right, and that will basically just give you powers of the number e. If you wanted your calculator to give you the number e, you could do e to the power of 1, basically. So you have an e to the power of x button. You could just use x is equal to 1, and it will give you the number e. So what we're going to do here is we're going to ask a question about this function. The question is, well, what is the inverse of this function, y is equal to e to the power of x? Well, since it's an exponential function, we should have some idea that the inverse of this is going to be a logarithmic function. And what we're going to do is we're going to talk about what the inverse of this special exponential function is. So remember that to take the inverse of a function, what we're going to do is we're going to start by swapping the location of the x and y variables in the equation. So that's going to give us something that looks like this. So x is equal to e to the power of y. And what I'm going to get you to notice is that this is written in exponential form. Right? So if you compare it to what we have written above in terms of exponential form, you'll notice that it's basically the same. And the other thing I'm going to point out to you is that technically by swapping the x and y variables, we've already got the inverse. So this is the inverse of the original function that we started with. It's just that we usually don't like to write the inverse of a function in this form. Usually we like to have y isolated for. So that's basically what we're going to be doing next. Now, in order to isolate for y in this expression, what we're going to need to do is we're going to need to basically make use of the change between exponential and logarithmic form that we just discussed above. So since this is written in exponential form, I can convert it to logarithmic form. And notice that since the base of the exponential is going to be e, that means that the base of my logarithm, when it's in logarithmic form, is also going to be e. And that means that we're going to have log base e of x is equal to y. Now here's the thing. E to the power of x is a very, very important function. And actually, a log with a base of e is also going to be very, very important. In fact, it's so important that it's got a special name. The logarithm with a base of e is going to be called the natural logarithm. And because it's special, we have a special symbol for it as well. So whenever you see log base e, or whenever you're working with log base e, I guess, you're actually not going to see log base e, you're going to see another symbol. Since it's called a natural logarithm, we use the symbol ln instead of log base e. Now usually when we have that, we don't pronounce it ln. A lot of times you're going to see it pronounced as the word ln. So for example, I can take what we wrote and rewrite it as y is equal to ln of x. And that's just the natural logarithm of x. In other words, we have y is equal to the log base e of x, but we just write it like this. Okay. So what's important here, right, is that if we want the inverse of y equals e to the power of x, right, then we're going to get y equals ln of x. In other words, y equals e to the power of x and y equals ln of x are inverses of one another. And that's going to be pretty important for a couple reasons. But what we're going to do, right, is we're now going to take a look at some properties of the natural logarithm. All right. I know that you've dealt with logarithms in the past, but since we have a special logarithm with a base of e, it might be helpful to look at some properties. And I think we should start with the graph. So the graph of the natural logarithm, well, again, we're basically graphing y equals ln of x. The base of the natural logarithm is going to be e, which is approximately 2.718 or so. And that means we're going to have an increasing logarithmic function. So it's going to look something like this. Right, couple important points about the way the graph is going to look. The domain is going to be the set of real numbers such that x is greater than 0. All right, so no negative numbers, right, for x values, and x is also not going to be equal to 0. The range of the function is going to be all real numbers, so y is an element of the real numbers. The x-intercept is going to occur at 1 and 0. The y-intercept, well, there isn't going to be one, and that's, of course, going to be because we have a vertical asymptote, right, at x is equal to 0. All right, so that would be properties of the graph of the natural logarithm. Okay, well, what about maybe some algebraic properties? Let's take a look at some of those. So the first algebraic property I want to discuss, okay, well, what if we have the ln of e? Okay, well, in this case, since the base of my logarithm is e, and since I'm taking the logarithm of the number e, that's going to just give us the number 1. All right, secondly, if I have something like ln of b to the power of a, in other words, if I'm taking the ln of an exponential term, but the base of the exponential term is an e, right, I have something else, well, I should actually be able to apply the Power Law of Logarithms to this. And if you recall, the Power Law of Logarithms basically means I can take the exponent a, and basically it drops down in front of the logarithm. So I have a times the ln of b. Okay, next, what if we have the ln of a product of two numbers? So in this case, we're taking the ln of a times b. Well, this is going to be something called the Product Law of Logarithms, which I'm assuming you've discussed before. That means that we should be able to rewrite this as the ln of a plus the ln of b. Now, the one thing I should point out to you is that this rule is only going to work as long as a and b are both positive numbers. Okay, along the same lines, if we're taking the ln of a over b, well, in this case, right, we have what we call the quotient rule of logarithms, and that means I should be able to write that as the ln of a minus the ln of b. And just like in the last case, right, this is only going to work, right, as long as both a and b are positive numbers. Next, what if we're taking the ln of e to the power of some number b? Well, in this scenario, since I'm taking the ln of an exponential term with a base of e, and also, since the natural logarithm and the exponential function base e are inverses of one another, they're going to be essentially acting like operations that undo one another. And that actually indicates to us that the result of this expression is just going to be whatever b was. And along a similar line, if I have e to the power of the ln of b, well, again, I have an exponential with a base of e, and I have a natural logarithm, which is a logarithm with a base of e, and since I'm applying them to one another, that means it's almost like you're going to cancel each other out, and this is going to just result in the value of b. Now, this last rule is going to be something that we're going to be discussing again in a little while, not in this video, but probably in the next one. And the reason why we're going to be discussing this rule, or using this rule, is because we're going to use this to find the derivative of f of x is equal to b to the power of x. Okay, the last thing I kind of want to go through with you in this video is I want to go through a brief example, right? In this case, solving an exponential equation with a base of e. Just because I know it's, for some of you, it's been a little bit of time since you've worked with exponentials and logarithms and so on. So let's just do a quick example. So let's say I have this, this equation, 2 times e to the power of 4x is equal to 10, and I'd like to solve for x. Okay, so the first thing that we would have to do here is we would have to take the 2 in front of the e to the power of 4x, and I'd want to divide both sides by that 2. Okay, well, dividing out both sides by 2, that's going to give us e to the power of 4x is equal to 5. Okay, and now in order to get access to that x, I'm going to need to make use of some logarithms. Well, since my exponential is with a base of e, it might make sense to use the natural logarithm in this case. In fact, what I can do is I can essentially take this, which is an exponential form, and convert it into logarithmic form with a base of e. And that means it's going to look something like the ln of 5 is equal to 4x, right? So that's just converting into logarithmic form. but of course it gives us access to that x that we're trying to solve for. Okay, so from here, what we're going to need to do is we're going to need to get rid of the 4 in front of the x. Since it's multiplying, we can divide both sides by 4, or if you prefer, you could multiply both sides by 1/4, and that's what I'm going to do. So that's going to give us 1/4 times the ln of 5 is equal to x. So this is actually a perfectly good exact form solution for x, 1/4 times the ln of 5. Okay, but of course there are a couple of things that we could do to maybe rewrite this in a different way. So I could also write this as the ln of 5 to the power of 1/4 is equal to x. And what we're doing there is we're making use of the Power Law of Logarithms. So since I have a coefficient of 1/4 in front of the logarithm, in this case in front of the natural logarithm, I could take that and apply it as an exponent to the number 5. Now, the one other thing I guess I could probably do here is since I have 5 to the power of 1/4, I can write that as a radical. So I might write this answer instead as the ln of the 4th root of 5 is equal to x. Now, all three of these last lines here, these are perfectly good exact form solutions for x. They're all great. Okay, well, what if you wanted to come up with an approximate solution? Well, again, if you look at any scientific calculator, right, you're going to see a button probably close to the logarithm button, and also near that button that has that e to the power of x on it. And it should have ln, the natural logarithm. So what we could do is we could actually calculate the value of x here using our calculators, right? Using, to be honest, any of these three last lines that we have here we could plug in. And if we did that, we could get an approximate solution. And our approximate solution should be about 0.402 for x. So that's how we can get an approximate solution to x. Anyways, I just figured that it would be helpful to talk about the natural logarithm. I hope it's been useful. Take care.